All right, in this video, I'm going to cover chapter 1 briefly. So I'm going to go over math, the mathematical background, basic mathematical theories we're going to use to prove theorems and develop the algorithm from chapter 2. So, so in section 1.1, chapter 1 introduced 1.1. We're going to the review of the calculus. So here, starting from the definition 1.1, a function of f defined on a set x of real numbers has the limit L at x0, x naught, written as like this. Yeah, I believe that all of you know about the definition of limit, but here um, we the actually we're gonna see more precise definition of the limit. So using it is called the epsilon delta theorems. So the limit of f of x as x approaches x naught equals L. We know that this is the limit of f of x equals L. Um, if given any real number epsilon is greater than 0, there exists a real number delta such that f of x minus L is less than epsilon whenever x is in the, the domain of function f of x, and x minus x naught is between 0 and delta. So I know it looks like it's hard to understand this. You may see this definition when you take a real analysis, but or you already saw that definition. You have heard this definition when you study calculus. All right. So the that means this as whenever x is close to x0. So it's x minus x naught, the absolute value of x minus x naught is between 0 and delta, means that the the x is within x minus delta and x naught plus delta. Okay, so let's say x is right here. Okay, so the x is x minus x naught, which is distance between x and x naught is less than delta, means that x is in within lies within x naught minus delta, x naught plus delta. Then the f of x, which is a function value of x naught, is also the close to L. So how much close to L? This much epsilon. So there exists epsilon. So it means that as x approach x naught, then its x function value f of x also close to L. That's the meaning of this definition. Okay, so if you wanna the interested in this definition, then just search the precise definition of limit in calculus book or yeah, calculus book. Okay, and now we move to the next one, next page. So definition 1.2. So using the definition limit, can define we could define the definition of continuous, right? So let me skip it. And then 1.3 converge. So a sequence converges to x means that the limit of sequence as in the index of sequence approaches infinity equals x. That's the definition of the limit of the sequence. So let xn be an infinite sequence of real number. This sequence has the limit x, or we can say converge to x. If for any epsilon there exists a positive integer n of epsilon, it means that what that means. This means it means this. There exists a positive integer n of epsilon. Means the positive integer n depends on epsilon. So depending on epsilon, the integer n depends on epsilon. That's the meaning of that symbol n of epsilon. So now then such that xn minus x is less than epsilon, it means that the xn is close to x. Okay, normally epsilon is a really small number, 0.00 or something like that. And whenever n is greater than n of epsilon, so whenever n is greater than the positive integer n, depending on epsilon, there exists there exists what the past integer n. Okay, so whenever n is greater than n, the limit of xn, whenever n is greater than n of epsilon. Sorry. So now theorem 1.4: if f of x is a function defined on a set x or real number, normally x means that the domain of f of x, then the following statements are equivalent. F is continuous x0 means that the sequence, if sequence is any sequence of x converges to x naught, then limit of f of x naught is equal to f of x naught, f of xn, and limit of f of xn equals f of x naught. Okay, so it means that the f is continuous means that what the continuous x naught means the function of the sequence converges to the function of the um, what the x naught, which is the limit of sequence. Okay, so now next one, differentiability. So give me a second. Yeah. Okay. So remember the definition of differentiation. So limit of f of x minus f of x naught over x minus x naught. That's the definition of f prime of x naught, right? So I believe you know I believe you know that one. It's okay. And then the geometrical meaning of the derivative is what? Tangent, slope, tangent line. Now the role theorems. If suppose f is belong to C in the closed interval a comma b, it means that this function is continuous on the interval a, closed interval a comma b. Okay, so and the f is differentiable on open interval a comma b. If f a is equal to f of b, then number c in a in belong to the interval a comma open interval a comma b, they're equal to c, such that f prime c equals 0. Okay, so it may what the rule theorem is this. As you can see that, let's say the graph of the function f of x is given like this. Okay, like that, right? Then f of a is equal to f of b. F of a is f of b, and then function f is continuous. There is, it means that there is no break and there is no jump. Okay, then the function f is differentiable. It means the function is really smooth. Then it should have what you should have certain x value, let's say c, such that f prime equals 0. It means that tangent line, slope of tangent line going to be equals 0. Because you think about this, when you draw the graph from starting from f of a smoothly, there's no the corner point and break or jump. Then and then back to the f of b, to that f of b equals b, f of b equals f of a, then the some at a certain point the graph must be turned down, right? So it's been turned down like this. Okay, so when you turn down, there it should have what it should exist the x value such that the slope of tangent line equals 0. Okay, that's rule theorems. Now next one. Uh, Mean value theorems. Mean value theorem is this. That's the general version of Rolle theorems. So f of the function is continuous on the closed interval ab, and then differentiable open interval ab, but we drop the one condition, one assumption in the Rolle theorems, such that which is f of a equals f of b. So f of a is not necessarily equal to f of b. Okay, then what happened? Then there exists certain x value c such that what the slope of tangent line f prime c, slope tangent line f prime c at x equals c is equal to what the secant line passing through the two endpoint f a comma b. Okay, you see this is secant line right here. This is secant line, and this what's the slope of the secant line? The slope of that secant line is this, right? This one. Okay. and then they're equal to c, such that the slope on tangent line, which is f prime c, is equal to the slope of that second line passing through f a comma f of a and b comma f of b. That's some beam veil theorems. Now, next one, extreme veil theorems. All right, so extreme veil theorem is f function f is continuous on closing number, and then c1, c2 belong to the closing number ab. Egogist, their egogist c1, c2 with f of x is between f of c1, f of c2. Okay, so look at this graph. So definitely the absolute maximum is f of c2, absolute minimum is f of c1, right? Okay, so now then in addition, if f is differentiable on opening number ab, then numbers c1 and c2 occur either at the end point of closing number ab or where f prime is 0. That's the how to find out absolute maximum minimum in calculus 1. So when you find out absolute maximum minimum, we gotta find out what critical point. How can you find the critical point? We find out what solution of the equation f prime equals 0. So see that c1, c2. So see c1, c2 actually critical values, right? So, and then we evaluate function at c1, c2, and then we evaluate function at the end points of given number, f of ab, and then maximum of, I mean, we find the maximum or minimum of those four values. That's going to be absolute maximum and minimum, right? So this is extreme value theorems. So now next one, let's see, generalized rule theorems. So generalized rule theorem is excuse me. The f will belong to the f is continuous and closing number, okay, and the n times differentiable. So we're not talking about just a graph of function f of x, but we think about the n times differentiable. N times differential means the derivative f is also the differentiable. The second derivative f is also differentiable. Okay, okay. Onto what? N times differential means that we can find out n uh, n's derivative of f. Okay. So now f of x equals 0 at n plus 1 distinct numbers. What does that mean? Then it means that the f of x equals 0 at the n plus 1 distinct numbers, then in the number line like this, okay, let's say this is x0, right here, and then here is x1, and then here's x2, okay. So graph must be, then function is continuous, and then n times differentiable means the f is really smooth, okay, there's no jump and then break, okay, there's no corner point. Graph must be like this. uh, like this, okay. So, and then the number c in x0 to x0 comma xn, there is number c, okay, there's number c, let's say here's number c, and hence in a comma b exists with the f n's derivative c equals 0. So then if a function f is continuous and then n times differentiable, and then there exists n plus 1 distinct numbers x0 through the xn, which are what actually what x coordinate of x intercept, right? These are actually x coordinates of x intercept, right? Then there exists c, maybe c is right here, and then I mean, let's say the nth derivative of f, let's say like this, okay. Then we see there is right there c. This is a c here, such that nth derivative of f. This is graph of f. Nth derivative of f. Okay. So now that's a generalized rule. It makes sense. You see. Let me just give you an example. Then think about this. Let's say just think about the quadratic function. Okay, function here. We know the derivative of f gonna be this. Uh, mm, like this, right? So this is the first derivative of f. Okay, And then what? That's gonna be x naught, right? That's gonna be x1 right here. And then right here, that's gonna be c. Now you understand it, right? So in this example, function f has two distinct numbers. Actually, two distinct what? X coordinate, x-intercept, x naught and x1. And then f is continuous. Closing number ab. Let's say here's a. Let's say here's a, okay? And then let's say here's a b, okay? Then closing number ab, the function is continuous, and then this is one times differentiable, right? One times differentiable. Actually, not one time. Actually, second time. I mean, infinite times differentiable, right? Derivative of a quadratic function is what? Linear function. Derivative linear function is a constant function. Derivative constant function is zero. Still constant function defined by zero, right? So actually basically every single polynomial function is infinite times differentiable. Okay, so but anyway, back to this topic. So then see, actually f of c is actually what? That's the actually critical value of the function f, right? Because in the c, the slope of tangent line is zero, right? Okay, so that's the general rule theorems. So there exists c such that the first, in this example, first derivative f equals 0. Now then, intermediate value theorems. So intermediate value theorems is this. F is continuous, and then k is any number between f and f of b, then there exists number c such that f of c equals k. Yeah, so is this. As long as the function is continuous and closed interval, then whenever you pick the function pick a number for function value, there exists x value corresponding to that number k. That's the intermediate value theorems. How can you guarantee that there exists such a c? Because the function is continuous. Okay. Because of that assumption, we can guarantee that there exists such a c, x value c, such that f of c equals k. Okay. For any choice of k between f of a and f of b. Okay. That's the intermediate value theorems. Now, next one. Yeah, so look at, keep in mind this is intermediate value theorems, and then generalized rule theorems, mean value theorems, and the rule theorems, okay? So this is really a basic theories we're gonna use a lot to develop the algorithm. Now, next one, definition of Riemann integral. Remember that Riemann integral? So when you define the integral, first, we chop this for this given function f. We want to figure out the area under the curve from the a to b. We chop the the interval, which is we chop the interval into n sub intervals, and then we build the strip rectangle, okay, like this, and then we find the area for each rectangle, adding them up. That's Riemann theorem, Riemann integral, right? So now then to see, and then we're gonna increase the number of integrals, number of the rectangles. So it means that we're gonna divide the interval more fine. Okay. So now we'll see. Next one is weighted mean value theorem for integral. So excuse me. All right, so we see. Suppose f is continuous, and the Riemann integral of g exists on closed interval a comma b, and g does not change sign of on a comma b. Okay, then there exists a number. Give me a second. Then there exists number c with integral of ab, integral of f of x times g of x between ab from a to b equals f of c times this. All right. So what does that mean? Okay. So let me see. So f is continuous, and then Riemann integral of g exists. All right. Then let's see. Let's see. Okay. Let's see. Okay. Now let's see this figure. Okay. So with by and then with g of x divided by 1. Okay. So now then, the integral of the f of x. Let's see. Let's see. Okay. To better understand the way to the mean value theorem for integral, we define g of x as 1. Okay, this is 1. This is also 1. Okay. Then that integral gonna becomes what? Just the just gonna be what, b minus a, right? Think about this. This is the x axis here and the y axis. Okay. And then here's a a, here's a b, and then there's a 1. I know there's a 1 right here. The integral of 1 from a to b is what? The area of that rectangle, right? What's the area of this rectangle? B minus a times 1. Width times height. So b minus a times 1, which is b minus a, right? Width times 1, so b minus a. So we move b minus a to the left-hand side, then we got this. F of c is equal to 1 over b minus a times integral of f of x from a to b. Now, what that means? So the f of c is right here. Okay, this is equal to, okay, integral of f of x from a to b, which is this one. Let me use other color. Yeah, this one. Let's see here. Okay, that is equal here times 1 over b minus a. 1 over b minus a. So 1 over b minus a is going to be what? Then here need to use a red one. Okay. Then we move the 1 on b minus to the left hand side. The b minus a times f of c is what? Actual rectangle, area of rectangle. That area of this rectangle is f of c times 1 over b minus a, right? Okay, b minus a. So f of c times b minus a, and then that is equal to area under the graph of f of x from a to b. That's the meaning of weighting the mean value theorem for integral. Okay, so now next one, the Taylor theorems. Oh yeah, this is also important. So f is nth cn. What does the cn? It means that function is continuous up to nth derivative. Okay, so f is continuous. Also, first derivative f is continuous. Second derivative continuous. Third derivative nth up to nth derivative f is continuous on closed interval ab. That's the meaning of cn. Okay, and the n plus 1th derivative, n plus 1th derivative of f exists. There exists. Okay, and the x naught is also belong to a comma b. Then for every x in closed interval ab, there exists number psi depending on x between x naught and x with this. So it means that for any type of function, exponential function, sine function, cosine function, any the non-polynomial function can be expressed as the polynomial function plus remainder term. This is a remainder term. That Pn is called Taylor polynomials. Taylor's polynomial defined by this: f of x naught plus f prime of x naught times x minus x naught through this. Keep in mind, this is, you have to memorize this. So we're gonna use this one a lot too. Okay. So we so this one in calculus 2, right? In calculus 2. Keep in mind this. So the for any type of even algebraic functions, non-algebraic functions, for any type of functions can be expressed as Taylor function from first truncation term. The R is called the truncation term. We can say that, or remainder term. Okay. So what's the remainder term? Is this. Okay. What is the cosine? Normally we don't know what cosine is because told that depends on the function definition function and the x value x. Okay. Now, okay. So please look at the example 3 by yourself. Okay. So read this one, and then that's the review of calculus. Yes, and then let's see. round off errors in computer arithmetic. So I posted a lecture note, one-page lecture note to round off errors. Okay, so look at it, or just you can read the textbook. Okay, so simply saying that let me see. Give me a second. Simply saying that round effort, you can read this paragraph in textbook, but round effort is this. So when computer just calculate the, in this example, for example, the 1/2, but the times, for example, 1/2 times √2. Uh, we know that 1/2 times √2 is just 1, right? But when you compute that 1/2 times √2 in using the computer or calculator, then they're gonna convert the √2 as a finite, the uh the real number with a finite digit. Okay, so then so so that the calculator or computer are gonna return not exactly the exact the what value 1, instead of that, see 1.00000 and 1, something like this, so that we're gonna get the error. That error is caused by the computation of finite digit performed by the machine, is called the round-off error. So you see that here, the error that is produced when calculator or computer used to perform the real number calculation is called the round-off errors. It occurs because the arithmetic performed in the machine involved the numbers with only a finite number of digits. That depends on the bit. Okay, 32-bit computer, the for this 32-bit computers, the um, up to 16 digit is called double precision. Up to 16 digit, uh, it's gonna be we're gonna get the exact value up to 16 digit, and then 64 bit is double, something like this. Okay, and then on the floor, and the overflow is, see, on the floor it is, if you get the so it's really small number that cannot that machine cannot handle. That's called the underflow. Overflow is really big number that machine cannot handle that. That all depends on the machine's performance and the software. Okay. So now so this the for the chapter 1. Okay, next video I'm going to cover 2.1.